Go to page 4, and let's try 8 through 15. So we said that the easiest things to do is order pairs, right? Get the order pairs out of the way because those don't require anything else besides the point. And then you can focus your attention on doing limits. And again, I want to remind you that if you ever see notation that says the limit does not exist, keep in mind that you have various options available to you, right? Everyone may interpret limit doesn't exist differently, but you want to make sure that you create a situation that is within acceptable bounds. So here again are the options. So let's say if I see a limit doesn't exist, you can either create some sort of an asymptote with the graphs either headed in the same direction or different directions. You can create an endpoint at 3 with the graph not picking up on the other side, or you can make it 2 disconnected branches. Those are all places, those are all situations you can create that would be where a limit doesn't exist. But what you don't want to do is you don't want to do this. If I had a hole with a graph connected to that hole, that limit does exist, right? So this is not the correct situation for limit doesn't exist. Now, I think what students may be thinking is when they do this, they're thinking, oh, the point doesn't exist, so therefore limit doesn't exist, which is not true, right? The point doesn't exist here, but the limit does exist because if I pick points on either side, both arrows are headed towards that hole. Yeah.
You ever been doing all the limits that do exist before you did ones that don't exist? Or is that?
Yeah, it's up to you. I don't I think we can create those situations both as easily as another. So it's up to you. And then whenever I see a limit that does exist, I always like to create a hole at that point and then just have extenders slightly out or coming out of those points. Sorry, guys, for 15, if you guys can change it to limit as x approaches 9, just so you give yourself more space. That 7 is really close to 6, and it's hard to get a graph going there. So for 15, if you can do x approaches 9, just kind of gives you a bit more space for us to work with.
What are these strong ones undefined?
I will leave it alone. Make sure at the end that nothing is there at the end of the problem.
Oh.
Okay, so let me show you my graph and see if yours is similar. Obviously, there may be rooms for interpretation, especially around limits doesn't exist. So here, for number 8, limit as x approaches -8 does not exist. So I purposely had a graph go to some y value at -8, but I did not extend it further from the other side. So I made it just an endpoint, and an endpoint is an acceptable way of representing does not exist. You could also do an asymptote there. You can also have disconnected graph on the other side, but a lot of options there. So number 9, my limit does exist at -7, -5. So I created a hole there, and I had graphs extending from both sides. But I didn't want to go too far because I didn't want to accidentally fail the vertical line test with another part of the graph. So I left that there alone for now. F of -3 equals 5. That's an ordered pair. That's easy. Limit as x approaches 4 equals 2. So I've started with a hole, and then I extended my graph slightly on both sides to I want you to take care of that immediate region and not go too far. F of 4 is undefined. That's still true because I have a hole there, so there's no need to fill in my hole anywhere on the graph. F of 6 equals 4, so I have a point there. Limit as x approaches 6 is infinity, and there's an asymptote there. Infinity means that the limit doesn't exist, but that infinity also tells me how I want the graph to behave. Both arrows are going to be headed up towards infinity. And then I have a limit that exists at 9, -3. So I created a hole at 9, -3, and I had graphs that extended. And I just decided that I was going to connect these two together. Some questions that students had was, how is it possible that there's an asymptote here and I have a point living on the asymptote? So just keep in mind that these are piecewise functions. There's no one function that's defining the graph that we see in front of us. They're all different functions that are kind of put on top of each other. But we can still call this a function because everything still passes the vertical line test. So even though there's no graph that can ever have a point on the asymptote, it's another graph that's defining the point that happens to be on the asymptote of this graph. But there's no conflict here because there's nothing that lives on this asymptote except that point. So it still remains a function.
So you can extend a line on the very bottom left, so like connect to the other one because then it won't pass the vertical.
You can. I mean, I think I have.
Points don't matter.
Not necessarily, yeah. So I think you can decide that you want to connect to this point if you want, and we're not breaking any rules if we did that. And then, yeah, you want to do it that way, yeah.
So the points connected and not connected, it's like up to your interpretation.
It's up to you, yeah. As long as they're not overlapping like this, right? Then we have an issue. Right? So at the end of the problem, you should always, at the end of your graph, you should always just imagine yourself, can I convince myself that no matter where I draw a vertical line, I'm not going to hit more than one point? Because if you can convince yourself of that, then you know you've passed the vertical line test. Yeah.
But is it an asymptote on like -8?
Yeah, that works. You can do that as well.
But do you just make the arrow go up or do you have to do it?
It doesn't matter. Yeah, you have a lot of options. You can make the arrows go in different directions or the same. So if they say limit doesn't exist, you have a ton of options, but just make sure you're choosing the correct option. Okay, good. Any other questions? Okay, so let's look at algebraic. So algebraic is the more involved one. So we'll be spending today and tomorrow exploring it, and then hopefully we can get through by midway tomorrow so we can do our quiz review. And I have 2 quiz review worksheets for you. So okay, so here's it says 1.3, but yeah, still trying to merge my notes from last year with this textbook, and so some of the numbers are a little bit off, but technically this is 1.2. Okay, so evaluating limits algebraically. There's a couple of rules here, but I'm going to skip these rules. It feels confusing. I think once we see examples, it'll make more sense. But here is the first rule of limits. This is an important rule because it's easy for us to skip this step because sometimes we think we know where the problem is headed and we skip this step, but don't skip this step. This is an important step. So if you want to find limits for a function algebraically, first try to evaluate that argument in the expression. So the first thing you do is you plug in that value. So imagine, like I said, you're just plugging the x into the function to get the y value. So you're going to just treat it like finding the y value. Okay. If the resulting value is a real number, then that value is the limit. So if I can plug in the value and get a number in return, then that is guaranteed to be my limit. It's going to be a continuous function. That point exists, the limit exists. There's nothing more that needs to be done. Okay, so if I can't get a real number out of direct substitution, then my problem stops. I have my answer. Okay, so here are some examples where that is going to work. So limit as x approaches 2 of x squared plus 3x. Just imagine, like I said, if you're inserting 2 into the function to get the y value. Okay. What do we get?
Good. 10.
10. That's a real number, right? So there's nothing more to do. The limit exists. The problem ends.
You plug in whatever like the bottom number is.
That's right. Yeah. So you're going to treat this the same way as if it was, if f of x was x squared plus 3x. And if I want to find f of 2, it's going to feel the same process for now. As long as you get a real number, it's like as if you're finding an ordered pair on the graph. For now, but on the quiz, no calculator. I would prefer us to not use calculator so we can practice this without a calculator. Okay, so -1 gets inserted for all the x's. So -3, -2, -7 plus 4.
Did you draw like a piecewise function after?
I'm sorry.
You did draw like a to get the function of equations after you're done. You know, number one equal those two equations.
Oh, no. I just want to kind of show you. This is the same thing as if you were to evaluate a function at 2. So we don't do that now. Okay, so that's our limit, right? It's like as if I'm plugging -1 into a function. Hey, what about B? I'm sorry, I skipped here. I should have went A, B, C, but this one here.
Does not exist.
Does exist. Just 5, right? There's no variable for me to plug in. So my function value will remain 5 the whole way through. So basically, this is just a horizontal line, right? That horizontal line, no matter where I am, it's going to stay that y equals 5 the entire way through.
Unit circle.
Yeah. So here, limit as x approaches pi of x cosine x. Replace pi for all the x's. What does that give us? Pi times -1, yeah. Which is just -pi. That's a real number as well. So as long as we get real numbers in return, there's nothing more that needs to be done. That's an easy process.
You need a unit circle to do that one, right?
Yeah. Cosine of pi is -1. Okay, so not all problems will be this easy and straightforward. The more interesting ones are the ones where we know there's a hole in the graph and we're trying to go through. So this is called the simplify reduce method, where we factor, simplify, and substitute. So here's the idea is that let's say we try to evaluate the argument, okay, much like how we did here, right? Do direct substitution. But let's say we get a 0/0 in return. So 0/0 means that there's a hole in the graph. It means that when I try to plug into this function, it's giving me an undefined point, but if I get a 0 over 0, it means that even though the point doesn't exist, the limit will exist. We just have to figure out where the arrows are headed. But we're doing this without the use of a calculator. And here's the way that we're going to approach finding the limit for this graph without the use of a graph. So the first thing we have to recognize is if we get that 0 over 0, just imagine yourself knowing, or just imagine the graph with a hole in it, but then the limit, existing. So if we get 0 over 0, it doesn't mean that the limit is undefined. It means the point is undefined, but the limit does exist, but we're still we're still unfinished with the problem. It's true that the function value is undefined because there's a hole in the graph, but the limit does still exist. Okay, so what we're going to do is we're going to try to factor, reduce, and simplify. We're going to try to find a way to remove that hole from the function and then reevaluate the expression so we can get down to a real number, and then that real number will tell us where that limit is. Okay, so let's walk through those steps here with A and B. All right, so first things first, we're going to do direct substitution because we don't know what's going on here. We don't know if it's a real number. We don't know if it's a hole. Okay, so first things first, replace every x with -2. That's always the first step. Okay, we don't want to skip that step. Okay, and what do we get? 0 over 0. Now, there's something that I want to point out to you about College Board, especially with limits. They don't like to see equals 0 over 0. So the workaround is do arrow equal over 0, arrow 0 over 0. The reason why they don't like the equal sign is because we can make an argument that 0 over 0 is not equal to this, and it's a whole issue. So we just say, hey, if we can just somehow avoid being caught with points taken off, just use an arrow. Right, now, I'm not going to take off any points if we use equal sign, just to let you know that with limit problems, or actually with any Fourier response questions, if we just use arrows all the way through, because the reason why they're picky about equal signs is if College Board sees an equal sign, or if the grader sees an equal sign, they're supposed to look at both sides of the equal sign and make sure that they're exactly equivalent to each other. But a lot of times we don't use equal signs that way, right? We use equal sign to indicate this is my next step, but I'm not committing that they're the same. But when they see an equal sign, they take it very literally. So I'm not, it's not going to be an issue for me when I, on my test or my assessment, but just to let you know, this is one of the picky things that College Board has.
So if you put an equal sign in test, you can mark a whole pair wrong, even though you're.
No, it'll be a case-by-case basis. They may take a point off because they say that both sides, they're always trying to give partial credit. So they're never going to take a whole question problem off. If it's like worth 9 points and you made that one little mistake, at most they'll take off like 1 point. Or half a point, but it depends, right? They have a set of rules that they follow. So whenever you get 0 over 0, you know that we can't say the limit doesn't exist. The limit does exist, but we're not there yet. We're kind of like at an incomplete stage, right? So, but we do know that there is something causing that hole. So we have to find a way to remove that hole. So we're going to look to factor, okay? So maybe if we can factor, we can see something that will appear in the numerator that will match the denominator. We know the x plus 2 is not going to go anywhere. So really that's a hint. That's a hint that there's an x plus 2 hiding in that numerator that's going to allow us to reduce and reevaluate. So if I factor x squared plus 5x plus 6, I ask myself what two numbers multiplies to be 5, and those same two numbers add up, multiplies to be 6, and those same two numbers add up to be 5. What are those numbers? X plus 3, x plus 2. So now we have the culprit, right? These are the ones responsible for causing that 0 over 0, making it difficult for us to make our initial evaluation. But now that we have common factors, we can remove it. If we remove it, we now have a simplified version of the graph without the hole in it. And then we're just going to reevaluate. What's my reevaluated limit? Okay. So plug -2 in for x, what do we get? 1. So that is the limit. That's where this graph, that's where that hole is that initially we couldn't read. So what's happening is that this is turning this graph into one without the hole. And then once it creates a version of the graph without the hole, we can then reevaluate and find out where that hole was located, which is where the limit is.
How does it doesn't equal 0, 0 at the beginning? What would you do then?
So we haven't gone to that yet, but right now you only have to worry about 2 options, either a real number or 0 over 0. Okay. We do have another option coming up with vertical asymptotes, but for now, up to the quiz is what we have for the quiz is just a real number or 0 over 0. Those are the only 2 options available to us right now, but we are going to have a little bit more to work with. Okay, all right, try part B. Oh, sorry. I just said that and I realized that that this is an issue that we have to worry about. Okay, sorry, I jumped the gun there. So let's try part B. Okay. Direct substitution. What do we get in the numerator? 12. And its denominator we get, okay, 0. So I just said that this wasn't part of it, but this is, my bad. There's 3 options. One option is real number. Second option is 0 over 0, which is a whole. And the third option is something like a non-zero over 0. Anybody know what's happening here? What's happening at 1?
Asymptote?
Yeah, it's a vertical asymptote.
What did you say 3 choices were? Real number, 0, 0?
Yeah, so real number, 0 over 0, and then undefined. So vertical asymptote, what do you know about a limit as we approach a vertical asymptote? Does not exist. Yeah, so we just say DNE.
You see anything other than 0, just that answer.
That's right, for now. After the quiz, we're going to go do something else, but up until the quiz.
And what if it's like 0 over a number? Then it would be a
Good. Yeah. So let me go through 3 scenarios involving 0, so that you don't get confused in terms of what they mean. Let's say I had 0 over 5. What does that mean? 0. Well, what's 0 over 5? What is the value of 0 over 5? If you see 0 over 5, what is that equal to?
0.
0.
It's 0. This is a real number. So if you evaluate a limit and if you get 0 over 5 or 0 over 12 or 0 over 16, that is a real number. You will say your answer is 0. If you get 0 over 0, we call that an indeterminate form. And that tells us that there's a hole in the graph. But the limit still exists. We just have to do more work to get to our answer. And finally, if you get 6 over 0, 10 over 0, 12 over 0, you know that this is undefined. And visually, you know that there is a vertical asymptote and that the limit does not exist. So that's why it's important that we always do direct substitution first, because we don't have the graph in front of us, but just by doing direct substitution, we can begin to create a mental picture as to what is happening there. Either it could be a continuous function, it could be a hole, it could be a vertical asymptote, and we can just narrow down our choices simply by doing direct substitution. Okay, let's do a few more here. Example 2. Direct substitution, right? Always the first step, right? We don't want to try to go too far into it. We don't want to just start factoring before. So even though I think this is what a lot of students want to do this, they see something that's factorable, they want to start factoring and then cancel out, right? So don't skip the step, right? And I'm also looking for you to show me that you're getting 0 over 0 before you go any further with your factoring. Okay, what do we get up top? Or what do we get here?
5.
Yeah, we get 20 over 4. That's a real number. And that's our answer. If we get a real number, there's nothing more to be done. We have our limit. We can end the problem and go to the next one.
Okay, so it's a real number, you just like, that's the answer.
That's the answer. Real number is the answer. Okay, part D.
Zero.
0 over 4, which is 0. Yep. Right.
Here's where to practice.
Yeah, let me yeah. Actually, let me see if I can start introducing you to the other type. So these practice are good, but hopefully we see the big picture, right? Big picture is if you get a real number, you stop. If you get 10 over 0, you also stop. It's a vertical asymptote. The only problems you got to go further is if you get 0 over 0. If you get 0 over 0, you factor, reduce, reevaluate, and you know in the end you will get a real number. Okay. Let's do number 5 here. Let's do number 5, and then I want to introduce you to the other 2 types that is meant for tomorrow, but I feel like we can just kind of get a head start. Yeah. No, oh, it doesn't have to be a whole number. As long as it's a fraction is fine too. If it's like, 13 over 14, that's also a real number. So it doesn't have to be an integer. As long as if it's a number over, if it's a rational number or fraction, that's fine as well. That's your answer. Yeah. Okay, let's try number 5. Okay, first things first, plug in -3. I get 9 minus 3 is 6. 6 minus 6 is 0. And denominator also gives me 0. Okay, so I know that what's happening here. There's a what? There's a hole, but the limit exists. Okay, limit exists. We are going to get a real number at the end of this process. We just haven't found it yet. But we don't want to stop the problem and say the limit doesn't exist. That's not true. The point doesn't exist, but the limit does. Okay, so, but looks like we have some factoring opportunities here. So multiplies to be -6, adds up to be 1. X squared minus 9. This is a difference of squares. These are both perfect squares. So I can do x plus 3, x minus 3. Yep. Okay. Do we see the culprit here? Yeah, the x plus 3s is what's causing the hole, right? So remove them. And then what do we do? Plug in. Yeah, plug into the remaining expression, and we should be left with a real number. That's a real number. That's our limit. That's our answer. Okay. Any questions so far?
So if you put the equal sign for that one, would it mark like?
That's fine because these are actually equal to each other, right? Because that's equal to that, so I'm fine with it. But yeah, you're right. I think the safest thing to do is just use arrows all the way through, and you're not going to accidentally get caught with them trying to catch you on that. But again, don't stress about it too much because I'm not going to take off points if you did that on the test. Just for future reference, when we get to free response practice problems in the spring, I'll remind you of this. I'll remind you, hey, just try to use arrows as much as you can throughout your free response question, just so that you don't get those points taken off for those small things. Okay. These are the more challenging ones. These are ones where we can't factor, but we have to have another just these unique or more involved ways to try to get the whole to show up and reduce for us. So this is called the conjugate method. So conjugate method is where there's radicals involved, but you're getting 0 over 0, but you still have to find a way to get the wholes to appear for you so you can cancel out. So let's look at example 1 here. Okay, but first things first, right? We never want to look at a problem and assume that something's going on. We always want to first do direct substitution. Okay, so page 7, look at first example here. If I evaluate my limit at 4, what do we get? Okay, it's definitely a 0 in the denominator, but numerator is also 0 because 4 in for x. 4 plus 32 is 36. Root 36 is 6. 6 minus 6 is 0. Okay, so we know there's a whole. There is a factor that's hiding in the numerator that we want to cancel out. The big hint here is that you see there's an x minus 4 here. X minus 4 is causing a 0. So we know there's an x minus 4 hiding in above that's also causing a 0. So our goal is we want to try to figure out, can we rewrite this expression so that we can get an x minus 4 to appear in the numerator so we can cancel it out. Okay, so the way that we can get rid of that radical easily, cleanly without changing the overall value is we can multiply the numerator and denominator by the numerator's conjugate. So the conjugate is the exact same expression as the numerator, but there's one slight change that we make. You know what that change is?
Like squared.
Even more simple than that. We're going to copy this exact same expression down.
Negative positives.
Yeah, the negative positive, but only change the minus between the two terms. Don't change what's inside the radical. Just change this minus to a positive. So 6 plus root x plus 32.
So keep 6 positive. You don't change that to negative.
Again, we only changed one thing. We only changed what's between. We're not going to change the entire expression. We're just going to change the expression in between. Because what's going to happen is this is going to allow for basically difference of squares, and things will clean up very nicely for us if we do that. Okay, so conjugate is this. Conjugate is if I have a plus b, the conjugate of a plus b is a minus b. So we're going to create basically a something that will factor or expand nicely. Okay, so conjugate term is just one where the sign is changing in between. We're not changing every term inside. We're just changing what's between the binomial. So now we're going to expand. Okay, so we're going to FOIL out the numerator. But you're going to see that if we FOIL this out, it's going to come out very clean. The radicals will disappear. Okay, so 6 times 6 is what? 36. And the next up here, 6 times root x plus 32. Okay, but then what's going to happen here if I do 6 times root x plus 32 and then a minus 6 root x plus 32? What's going to happen with the middle terms? Cancels out. So that's nice, which means that we can ignore the middle terms, just the outer ones. So we'll do 6 times 6, which is 36. And we can do root x plus 32 times root x plus 32. What's going to happen here if I multiply two radicals together?
X plus 32.
Yeah, but there's a slight adjustment we have to make. What's a negative times a positive?
Negative.
A negative. So we always want to protect that negative with the set of parentheses. Otherwise, we're going to forget that the negative is going to distribute through your new expression without the radical. The reason why is because they ended up canceling out. So let me show you up here. If I were to FOIL out this whole thing, it will look like this. It will be 36 plus 6 root x plus 32 minus 6 root x plus 32 minus root x plus 32 squared. So you see how these middle terms here? So that's why I ignored them because I knew that they were going to cancel out. So I just focused my attention on the ends. So the strategy here is you want to FOIL the numerator, but you don't want to FOIL the denominator. The reason why is because this x minus 4 is ready for you to cancel out. If you FOIL that x minus 4 out, you're going to lose that ability to see that x minus 4. So you want to leave it alone. Okay. And then the rest of the steps is we're going to clean this up, cancel out, and reevaluate and get down to a real number. Okay. So let's finish this up tomorrow. I just want to kind of get an intro into tomorrow. You guys have homework tonight. Check your calendar. Okay. And then we'll pick this up tomorrow. Finish those tomorrow. Start the quiz review. Thursday quiz review, and Friday's our quiz. All right, come get your phones.
Thank you.